Welcome to Modeling with Exponential Functions. So I know you might think that it's just about modeling when you see me, but it's actually about math too, okay? So remember, I put this copy of the note-taking for you so you don't have to write down all the problems, and we can speed through this so it's not going to be a 500 million minute video on exponential modeling, because I'm sure you have better things to do, but just in case you don't, you can slow it down and go half time. Okay, so we learned yesterday that exponential functions are anything that has a variable in the numerator. So most of our modeling things are going to be looking like this. So remember, A is the initial value and B is the base. But what we're really going to talk about is we really have what's called exponential growth when the graph is increasing, and we have exponential decay. So that would be if the graph is decreasing. And really, these are easy to figure out if it's growing or decaying. If you have exponential growth, you might have some initial value of, say, 500, and then something like 1.3 to the x power. That would be an exponential growth because this number here is bigger than 1. So anything bigger than 1 is going to make the function increase. So then exponential decay, maybe we have the same initial value, but we have like 0.8 to the x. So I know that this is decaying because this number here is less than 1. And if the base is equal to 1, it won't be exponential at all because 1 to any power is just 1, and you'll just end up with the same number all the time. So that would mean that if I'm looking at this, if my base is 1.3, we say that we have a growth rate of 30%. So the way I found that number was I just did 1.3 minus 1. I got 0.3, and then I just turned that into a percentage. So basically, like every year you're increasing your population by 30%, or every year you're increasing your salary by 30% or something. So decay, I would do instead of this number minus 1 like I did over there, I do 1 minus that number. So I have a growth rate of 20%, but actually this is decay. All right? So then you have some basic problems that you're going to see in your homework tonight that look like this. You see them on your paper. If you have an initial value, we're going to write all our functions like this. A times b to the x. So the first question says that you have an initial value, so that's y is equal to 500, and then you have a growth rate of 25%. So 25%, I just write that as 0.25, and then I just have to remember to make it a rate bigger than 1 because it's growing, I add 1 to that. So I would have 1.25 raised to the x power. So that's the first problem. Okay, then the second problem, or second example, your initial value is 728, so maybe start off with 728. And then it says that you are decaying at 15%. So I just convert that to a decimal, 0.15, and I do minus 1 minus 0.15. So my base would be 0.85. So my function for number 2 would be 0.85 to the x. So you can see the first one has a growth rate greater than 1, so it's increasing, and a growth rate less than 1, so it's decreasing or decaying. All right, easy. This is easy stuff. I can't wait till we solve them using logs. It's going to be really fun. A couple days. Okay, so here's the ones that people get confused on. We start off with 500, and you double it. So if this number is doubling every day, that just means that your base is, I don't know, if I double something, I'm really just multiplying it by 2. So that just means that my base is 2 to the x power. No big deal. Whoops, that's example 3. Example 4, I have an initial value of 1700, and I'm tripling something every... Oh, I forgot something. I didn't look very closely. I'm tripling here. Okay, so let's backtrack. Because this one says that it's 500. It doubles every 5 years. So if we make x t for time, just divide that by 5. Because then 5 divided by 5 is 1. And then in every 5-year interval, it'll be doubling by 1. So here, we're going to call x time, and this is triples every, I can't read my writing, 18 years. So I just have to remember however long it takes, I just divide my time by that amount. Oh, that's not so bad. So let's see, 5. Oh, I'm starting off with 50 grams of substance. I'm halving it, so that means my base is a half. But it's not halving every day, it's halving every 35 days. So I would just say t divided by 35, and then I would mention probably that t is a measure of days. Problem number 6. We're quartering, which is a real weird word. So a quarter of something is 0.25, but it's quartering every 20 days, so that would just be time over 20, and then t is equal to days again. And those first two, t would have been an example of years. So you have a bunch of problems like that you're going to practice in class. It's pretty basic. And then you're going to be writing these equations given some information. So let's look at this. I want to find the equation for an exponential function that has initial value 0, 5, and then passes through this point to 35. This is your next example. So how do I write the equation of this? Well, I know that I start at y is equal to a times b to the x. This is my initial value, so that's easy to plug in, 5 times b to the x. Now I just plug this point in over here for x, and that point for y. So let's see, 35 is equal to 5 times b to the second power. Now I divide both sides by 5, so I get that 7 is equal to b squared. So that means that b is equal to the square root of 7. Now because we're doing this in exponentials, we're talking about exponents, think about writing the square root of 7. Oh my gosh, look at my conic section is getting in the way. Think about writing the square root of 7 as a fraction, because that's going to be helpful in a second. So 7 to the 1/2 power. So then all I have to do is just put all this stuff back into my equation. So 5 times 7 to the 1/2 raised to the x. Oh, remember your exponent rules? When you have an exponent raised to another exponent, raised up high, you multiply. So 5 times 7 to the x divided by 2. All right? Now let's do the second example, and that's going to be of one that's decaying. So it's perfect that I have these graphs right here. So this initial value is 0, 3. And then a point that it goes through here is 4, 1 over 27. Uh-oh. I know what you're thinking at home. Fractions! It's not so bad. So y is equal to 3 times b to the x. Plug in this initial value first. And then I'm going to plug in this other point for x and y. So 1 over 27 is equal to 3 times b to the 4th power. How do you guys feel about that? Good? Okay, so now I have to isolate the b, which means I divide by 3. Dividing by 3 is the same thing as multiplying by a third. So I get 1 over 81 is equal to b to the 4th. And then I have to take the 4th root of this. But I picked out my numbers so perfectly because I know that 81 is really in disguise 3 to the 4th power. So when I take the 4th root of something raised to the 4th power, I just get that b is equal to 1/3. So then just write that into your equation. So 3 times, oh, here's something really important to think about. Can I just multiply these two things together? No, because this one has a variable attached to it and this one doesn't. And then just double check. Make sure that if your function's decreasing, that your base is less than 1. Here my function is greater than 1, so oh, look at that. My base is greater than 1, so my function's increasing. So it looks like I did those right. Okay, so last examples, you have a new sort of exponential model, and you have those funny little graphs there, and it's called logistic growth. Okay, so a logistic graph is like kind of like a funny little S, where in this region right here, basically this is still the initial value. So let's say that you have 0, 5 here, and let's say this is 1,000, and then it's going to level off to something right here, and then let's say you have 2, 500, something like that. So what logistic models represent is that this period in here, so like for a short period of time, something is going to be growing exponentially. So a great example is something like a rumor. If you start a rumor, or if people are gossiping and they're telling some story, on the first day, not really very many people know about it. But then that rumor starts traveling because, you know, I have my 5 friends, we all know. Our 5 friends tell 5 other friends, those 5 other friends tell 5 other friends. It's like huge exponential growth. So for a certain amount of time, it's growing exponentially. But then after a while, once you spread the rumor, eventually everyone's going to find out. So you can't, no more people can find out because everyone already knows. Or this works also in like populations of wild animals. Like there's just a certain amount of food that can sustain a population, so it's going to limit to a certain amount up here. So exponential models or logistic models look like this. C divided by 1 plus A times B to the X. So the C on the top is the limiting value. And then we're going to figure out these other 2 numbers in just a second. So the way that you start these is, first of all, this number on the top is always, that's going to be your C. So I'm going to plug that in first. So y is equal to 1,000 divided by 1 plus A times B to the X. Now, second step is, so this is step 1. Then step 2, I plug this in for X and Y, this initial value for X and Y. So I set 5 equal to 1,000 divided by 1 plus A times B to the X. Whoops. B to the 0, because X is 0. So B to the 0 is 1. So this is really the same thing as just writing 5 is equal to 1,000 divided by 1 plus A. Now what I'm going to do here is just use the properties of cross multiplying. So I'll get 1 plus A is equal to 1,000 divided by 5. So 1 plus A is equal to 200. So I get A is equal to 199. Does that make sense? So that looks pretty good. So then I'm going to plug that in right there. So right now I have Y is equal to 1,000 divided by 1 plus 199 times B to the X power. So the second thing that I need to do is solve for B. So that's when this other part comes in right here. So step 3 is plug in the final point that we haven't used yet. So Y is equal to 500 equals 1,000 divided by 1 plus 199 times B squared. I'm going to do my little trick. So I get 1 plus 199 B squared is equal to 1,000 over 500. So 1 plus 199 B squared is equal to 2. Subtract 1 from both sides, I get 199 B squared is equal to 1. And this is where you need to get out your calculator. You're going to have to do this work for me. I get that B squared is equal to 1 divided by 199. So B is equal to this. I'm going to just leave it raised to the 1/2 power. I'm going to leave it like that because I only have pens in my hand and I don't have a calculator. So now all I have to do is just take this and plug it back in. So my final equation turns out to be, get it? B, oh no, you could listen to me all day. Okay, so 1,000 divided by 1 plus 199 times 1 over 199 to the 1/2 raised to the x power, so that's to the x over 2. Now if you had, I always run out of room right there. If you had a calculator, you could just take the square root of 1 over 199 and write this as a decimal. It's going to be a really small number. These are always really small. So you have space on your paper to practice one more of those logistic ones. So I want to see if you can do that on your own. And I'll be checking your work tomorrow. So let me put the points in there for you. So on the second logistic function, I'm going to give you smaller numbers. This limit to growth up here is going to be 200. Your initial value is 0, 4. And then a point there is going to be 5, 100. So why don't you guys try, C divided by 1 plus A times B to the X. Try that for your other curve, and I'll be checking you tomorrow. Okay, I hope you had fun with exponential modeling. See you in class.